Welcome to a series of lectures on mathematical finance. We will begin with the basis of mathematical finance, understanding of basics. This is quite hard and long course, but after learning this course, you will be able to price derivatives and be a successful quantitative analyst. Let's begin with definition. Definition. Assume we have a function or mapping from the set x to another set y. And in this mapping, element small x from this set big X maps into another element f of x, which is inside set big Y. And this mapping f is called injective. Injective. When by definition we have, if x is not equal to y, then f of x is not equal to f of y. That's why we can say that different elements are mapped into different elements in y. Once again, different elements in set x are mapped into different elements in set y. In this case, our mapping is called injective. Next, our mapping or function is called surjective. Surjective, by definition, if for any, this symbol means for any y in set big Y exists x small x in big X here, such that y is equal to f of x. In this case, this mapping is called surjective. In other words, for any element y, we have some x such that y is equal to f of x. So any element here in y has some element in x such that y is equal to f of x. Next, our mapping is called bijective. Bijective. If by definition our mapping is injective and surjective. So mapping is called bijective if this mapping is injective and surjective. What does it mean in practice? In practice, it means that our bijective mapping is so-called one-to-one correspondence between two sets. For example, if we have some set X and our mapping maps our set X into another set which is big Y. So these elements of set X is mapped into these elements of the set Y. And when we have bijective mapping, in this case, we have one-to-one correspondence between these two sets. Why? Because if we do not have one-to-one correspondence, for example, if we have this, in this case, one element is mapped into two elements. This is not a function. This mapping is called bijective, and as I said, this is one-to-one correspondence. And we do not have a situation when two elements, this element and this element, are mapped into one element. Because this is bijective, and by definition, this is injective and surjective. And injective means different elements are mapped into different elements. And that's why these two elements cannot be mapped into one element. And from other side, we cannot have the situation when we have some element here, and we do not have any element in X here, such that this element is mapped into this element. Because this is surjective mapping, and for any X in Y, we have some, for any Y in big Y, we have some X such that Y is equal to f of X. That's why this situation is impossible, and we have to have some element here such that we have a mapping, and this element of x is mapped into this element of y. And that's why when we want to check is our mapping bijective, is this one-to-one correspondence, first of all, we check is it injective, and then we check is it surjective. Direct image f of a by definition is all elements f of x such that x in a. Direct image. Let's draw a picture. Assume we have some set x, and here we have set y, and some subset a is mapped into another subset f of a under this mapping f. In this case, f of a, this element, is all f of x such that x is inside, x is in a. So all x, here we have x inside a, are mapped into f of x inside f of a. That's why this is a set called direct image of the subset A. Next, we have definition of inverse image. Inverse image f minus a of b, of some set b. Let's draw a picture. Assume we have some set y, and this set y is a result of mapping f from another set x. And assume after this mapping we have some set b inside y, and this f minus 1b is all elements x such that after this mapping are mapped into this subset b of y. That's why we write it as in mathematical, using mathematical denotions. This is all elements small x in x, all elements here, such that f of x is inside b. So all elements here such that after mapping are transformed into elements of b called inverse image. This is a subset inside set x. This inverse image is also called pullback. We have very important relations for this inverse image or pullback. Let's begin with the first. The first is that f minus 1 of a intersected by b is equal to f minus 1 a intersected by f minus 1 of b. Or in other words, pullback of intersection is intersection of pullbacks. This is quite obviously, we can prove it using very obvious explanation. We have to just prove that any element here is inside this subset, and opposite, any element in this set is inside this set. If we draw a picture, we have some set x is mapped into another set y, and here assume we have some a and b, and this is an intersection. This is an intersection. This is a intersected by b, and these sets a and b have a pullback inside the set x, and this will be f minus 1 a. This is pullback of set a, and this is f minus 1 b. This is pullback of set b, and this intersection is f minus 1 a intersected by f minus 1 b. So pullback of intersection is equal to of intersection of pullbacks. Next, we have the same relation, but not for intersection, but for union. We can write here a union. Let's rewrite it, and we have f minus 1